Good morning to everyone. I'm Jhon Diezmos MANALO. I'm a PhD student in civil engineering, and today I'm glad to present the latest research outputs of our research group based at the Department of Civil Computer Science and Aeronautical Technologies Engineering of RomaTre University. My PhD tutor is Professor Fabrizio D'Amico, and we are glad to present this work during this important SIIV arena with the title of Monitoring Air Pollution and Aerosol Concentration using Single Photon LiDAR. This activity was done during the Getter's Hack Data Dive project held at the Technical University of Vienna. Air pollution from infrastructures and construction sites is a significant environmental concern with detrimental effects on human health and the environment. The study aims to create a 3D building information model, BIM, and measure aerosol concentration in the surrounding residential area using single photon LiDAR data. By understanding the contributing factors, strategies can be developed to mitigate and control emissions. This innovative approach serves as an inspiration for future study to fully validate and improve the monitoring of aerosol concentration levels, and potential monitoring techniques will be explored to assess air pollution levels and guide effective pollution management practices. The data used were collected on 29 of July 2018 with a Leica SPL100 laser scanner, and the flight mission parameters are given in the table below. The data owner is the city of Vienna, and the data acquisition was performed by COWI. The dataset used are two raw point clouds covering a residential and forest areas of Vienna. Both point clouds were preprocessed using the Opals software, and can we extract the noise, the forest, and the residential area from laser scanner data. This study aims at defining a viable methodology to be implemented for an integrated interpretation of single photon LiDAR data outputs collected by several sources into a single BIM model. The methodology of the developed approach is shown in this diagram, where we notice two main flows running in parallel and then rejoining in the purpose. All data were processed with Opals software, which is powerful and versatile software for processing airborne laser scanner data and uses a JavaScript programming language. Starting from the laser scanner noise data, the following steps were performed. An additional attribute called PT counts was calculated to extract the noise. Subsequently, the density of the point cloud was calculated within 5 × 5 cells with a vertical offset of 10 meters. Then, I calculated 14 layers of data for the forested area, ranging from 410 meters to 550 meters in altitude. Additionally, we considered 12 layers for the residential area, covering altitudes from 210 meters to 330 meters. The idea that these point clouds represent tiny particles in the air from natural and man-made sources that affect air quality, climate, and health, known as aerosols. It was tested using remote sensing data from the Sentinel-5B mission. The Sentinel-5B data used are Aerosol Index (AI), Absorbing Aerosol Index (AAI), Aerosol Optical Depth (AOD), Aerosol Layer Height (ALH). AI and AAI represent a measure of the prevalence of aerosol in the atmosphere. Firstly, it can be seen that the heights of our two study areas fall within the range of minimum to average aerosol layer height. Secondly, lower AI, AAI, and AOD values are found in the forest area, and they correlate with point density calculated from LiDAR data, whereas we have a higher point density in the residential area. These results don't prove that point density from single photon LiDAR data represent aerosols suspended in the air, but they point in that direction, and it is up to future studies to try to prove this by integrating more data into this approach. A visual representation of the average point density over all elevation levels is shown in the figure about the forest area. And in this another figure, a visual representation about the residential area where it is a very high point density or aerosol concentration. In the meantime, with the residential area point cloud, it was reconstruct a building information model, BIM, of the area, starting with the reconstruction of the digital terrain model. These points cloud were always processed through the Opals software. In this case, only the clouds concerning the terrain were extracted. Parametric objects were then modeled, such as the infrastructures and building in the entire area. This resulted in a complete digital information model of the entire study area. The BIM model will serve as a database for all previously processed data. The study successfully demonstrated the potential of using single photon LiDAR data in conjunction with the satellite-based aerosol measurement for assessing air pollution in urban areas. The correlation between point density calculated from LiDAR data and aerosol data from the Sentinel-5P satellite suggests a possible link between LiDAR point density and aerosol suspended in the air. While the results are promising, it's important to acknowledge that the study only points in that direction, and further research is needed to establish a more definitive relationship. The developed methodology, which involved the creation of a comprehensive building information model, BIM, and the integration of different data sources, provides a strong foundation for future study in the field of air pollution monitoring. This approach can be applied to other urban areas, enabling city planners and policymakers to gain valuable insight into air quality and pollution distribution. The BIM model, combined with the insight from satellite and LiDAR data, can support urban management and planning efforts, contributing to more effective mitigation of air pollution in infrastructure and construction sites. About the future developments, although this research achieved significant progress, there are still opportunities for improvement and expansions. Future studies should aim to integrate more data sources and increase the spatial and temporal resolution of the measurements, including data from multiple LiDAR scans, additional satellite mission, and ground-based air quality monitoring networks can enhance the accuracy of the assessment. Moreover, conducting long-term monitoring and comparison can help identify trends and establish a more robust link between LiDAR point density and aerosol concentration. As technology advances and new data sources become available, ongoing research in this area will likely yield valuable insight into air pollution monitoring and its implication for public health and urban planning. Overall, the study highlights the potential of combining different data modalities and emphasizes the importance of interdisciplinary research to address complex environmental challenges. By continually refining methodologies and expanding data sources, scientists and policymakers can gain a deeper understanding of air pollution dynamics, leading to more informed decisions to protect the environment and improve public health. So thank you for your attention, and this is my contact author. Thank you for